Okay, so we are approaching the conclusion of this workshop, and I'm Ilaria Perugia from Mathematics, and it's my great pleasure to announce the speaker, who is Irene Fonseca. Irene is professor and director of the Center of Nonlinear Analysis at Carnegie Mellon, and I promised not to go through her career. But I just mentioned that she was the president of SIAM, the Society of Industrial and Applied Mathematics, but most importantly, she's a friend of Vienna and a friend of the ESI. So she has participated in many workshops and programs, and she will be Senior Research Fellow in 2024 at the ESI in April. So she will be around here. She will honor us of her presence for almost 1 month, and she will also give a lecture. So she's expert in applied analysis with applications, especially material sciences and imaging, and this is exactly what her talk today will be about. So please, Irene.
Thank you, Ilaria. So, I have to start by thanking the opportunity to be here for this celebration. Every time I have the chance to come to Vienna, I do. And it's been, I don't know how many times I've been visiting this house, so it's been a pleasure. And yes, I will be teaching a course in April. So okay, so this is going to be an overview, as Ilaria just said, of my current interests in both applications from the point of view of PDEs and Cox variations, coming from, on one hand, material science, and on the other hand, imaging. So, this doesn't work, so I have to do it like that. So, well, these seem to be very different topics, but that's the beauty of math, right, is that if you step back, then often the same kind of models and the same kind of questions and challenges apply to very different contexts, and that's exactly what's going to happen here. So what they have in common, well, I will address both of them from the variational point of view. The two problems I'm going to address involve both bulk competition between bulk and surface energies, and in terms of the basically function analysis, the spaces where you work with, these are spaces where usually you don't have a lot of regularity. You may have jumps, so you may leave the comfort zone of Sobolev spaces and go to spaces like bounded variation and so on. So, so there will be two parts again to my talk. The first one, so let me give an overview, and this may be a bit optimistic, but anyway. So I will start with Cahn-Hilliard, with a very brief introduction to Cahn-Hilliard. And in here, you're going to have the coexistence of phase transitions with homogenization. So basically, you're going to work with models where you have two small parameters, epsilon and a delta. The epsilon is going to essentially be the width of the transition layer, where you go from one well to the other. So, and eventually it's going to disappear on you, and you're going to land on two pure phases, while delta will stand for the parameters, essentially the size of the grid, if you have an homogenization, a periodic homogenization, working together with the phase transition. Of course, you have two parameters, so we know that we are going to look at three different regimes. The first one is when they go in tandem, and I'm going to, again, in this first case, and I'll make more clear what I'm talking about, you're going to have two fixed phases. The second topic will be the supercritical case where homogenization occurs first, and then you have the phase transition. And by the way, these are all my collaborators. And the last one, which part of it is still in progress, it's the final regime where you first go to an interface and then you still have homogenization occurring on your interface. That is the most complicated case, but very interesting. And in here, actually, I'm going to consider the case where I have moving wells, and I will justify why I do that. Okay, so then switching gears, and I'm in Vienna, so I'm going to bring up about Viennese mathematics. Elisa, she's from Vienna. Actually, she was featured yesterday in Christoph's movie, and I had the privilege of having her as a postdoc at CMU years ago. So these are my collaborators here, and that's exactly, so this, in here we are going to talk about, again, variational approaches to image denoising, and it has a little bit of the flavor of what Gita's talked about this morning, so we'll see that happening. So, okay, moving on. A very brief introduction, so I'm going to make it simple. Imagine that you have a fluid that likes to live in one of two phases, either the phase here -1 or the phase 1. This is a prototype. Of course, it can be much more complicated than this, but basically you're going to have a spinodal to go for an energy barrier to go from one to the other, and you'd like to minimize the energy that's supported by this energy density. Now, if I just leave it like that, of course, you're going to have infinitely many solutions because anything, as we'll see, that only takes values 1 or -1 will do. More generally, you can assume that your container is in Rn. You can even take Q to be vector valued. It does not have to be a real value. I'm going to always consider fixed volume fractions. So basically, I'm going to give you, I want to have a fixed amount of -1s or of 1s at the end of the day. Again, it does not have to be -1 and 1, could be an A and B. And again, and this could be vector values. So, okay, so as I said, this is the problem that you want to minimize. Just as I leave it like that, you have infinitely many solutions. Basically, any characteristic function that just takes values A, characteristic in that sense, A in one set and B in the complement will have energy 0, provided the support where, say, U is equal to A has the right volume or measure so that the fixed volume fraction is satisfied. And so that goes back again to Kahn, Hilliard, van der Waals, and so on, that one way to resolve these non-uniqueness is to add interfacial energy. So, and that's where this term comes in, right? Because if you move from -1 to 1, you play with the gradient in a smooth way. And so these would be the usual singular perturbation problem where epsilon here is essentially the width of the layer when you go from -1 to 1. Okay, it does not have to be grad U, could be an anisotropic function of the gradient, could be a higher order, and so on. But again, I'm trying to keep it simple here. Okay, and so this goes back to my former colleague, no longer with us, Mort Gerten, and Mort Gerten's conjecture that, okay, so now if I consider this energy, and if I take minimizers for this perturbed energy, somehow they're going to converge in some sense to one of those characteristic functions, but now it's a special one. It's one that will minimize the perimeter, so the interfacial energy inside the container. So among all possible ways, all possible designs where you put A's inside the matrix B or B's inside the matrix A, you look at the contours, and the preferred one should minimize that surface energy. Now that has been made rigorous through the notion of gamma convergence in the calculus of variations. I don't want to go through that a lot, but basically you scale by epsilon, and scaling by epsilon the energy certainly will not mess up minimizers. They are the same, right? The minimizer of this is the minimizer by epsilon. And in the sense of gamma convergence, indeed, the limiting energy is one that it's the perimeter. So you have a function U that only takes two values, A and B. Its bounded variation just means that the interface, it's nice. You can basically assign a measure to that, a surface measure. So up to a constant, it's indeed the perimeter. A0 here is the phase where U equal to A, so that would be the same as the perimeter where U is equal to B. In this prototype example, the constant can be explicitly calculated like so. So, very briefly, but again, I don't want to go into this, the notion of gamma convergence has two parts to it. One is that if you have a sequence converging to you in some topology, the limiting energy should be below the limit inf. And this is optimal in that give me a target U and I can find what we call a recovery sequence U epsilon, which converges to U and you have the reverse inequality. So that actually have equality between these two. And what is beautiful about this notion of gamma convergence is that minimizers of the approximating sequence do converge to minimizers of the limit. So in this way, if I know how the gamma limit looks like, I have a selection criteria. Then I know that, okay, so then those minimizers will converge to a minimizer of this F, which in our case is perimeter, which is exactly what Mort-Gerten conjecture. Okay, this has been made rigorously. So again, Gerten's conjecture through gamma limit, that's a theorem that goes back to Modic and Mortola. So here are some references. By no way it's exhaustive. You can have all kinds of, for example, you could have the system coupled, you could have vector valued. It does not have to be quadratic. You can even consider higher order derivatives if you, instead of having liquid, you have solid. So nonlinear elastic materials existing in two phases, then this would be the strain, right? And so, and this basically captures curvature effects. Okay, but, so the point here now is that you pause and you think, oh, wait a second. So right now I'm considering this case where I have a double energy well, with wells are fixed, right? They don't depend on position. And it turns out that, first of all, the material does not have to be homogeneous, could be heterogeneous. So properties could depend on position. And not only that, but you could have an homogenization occurring at the same time. And there are examples going back, for example, to lipid rafts. This is taken from Science, an issue of Science, where these biologists were using basically Kahn-Hilliard to model these membrane properties of these lipid rafts. And what they said was that, oh yes, indeed, you should consider the homogenization where with this faster and faster inclusions of one material inside the other, and if you do that, actually at the first order you don't see phase separation. So I showed you that the gamma limit was surface was perimeter, which is surface, right? So you go from volume to surface, and they said no. At first order you actually should see volume. And you only see phase separation when you go to the next scale. So I'm going to try to convince you that that's indeed true. So again, this is a typical, again, taken from the same issue, a typical picture for those of you working on homogenization, that you start with your particles and then they become finer and finer, the grid is smaller and smaller, and in the end, you just get an homogenized material. And the question is, how can I deduce the properties of the homogenized material from the properties of the original model? Okay, so here it is. So you have Kahn-Hilliard, but now it depends on position, and this is a very fast variable here. I'm going to take W. Okay, eventually in the end I'll talk about the stochastic. This is deterministic. Eventually I'm going to talk about stochastic approach. So here, W is periodic, so you have a very fast oscillation here. And by the way, maybe the wells could depend on position, right? So they could depend on X. A typical example is one where, say, you have your periodic cell is the unit cube. You have a subset E where the energy looks like W1. On the complement, it looks like W2. And the reason why I'm putting that here, it's because this is essentially this is the prototype we have in our minds, in that the energy should not be more than measurable with respect to x, because it could jump, as in this case. Okay, and again, delta and epsilon go to 0. Delta goes depending on epsilon. Okay, so the first case is the case where they go in tandem, and here we proved that the gamma limit looks like, again, the original one that I showed you, is going to be an integral over the boundary of the phase A, but now it's an isotropic energy, while before you had a constant, so I pulled the constant out, it's just constant times the measure. Now it's actually an isotropic. It does depend on the normal. This is particularly interesting. Okay, the sigma, okay, there's a cell formula for the sigma, it doesn't matter. What I think it's interesting here is that, at least in my experience, normally when you have these singular perturbation problems, you end up with an isotropic energy if you start with an isotropic interfacial energy. Ours was grad square, which is pre-isotropic. So that is the first case I know where you end up with something which is an isotropic. And it's actually, it's a theorem. You can prove that it's an isotropic unless your problem is basically trivial. Okay, so there was another paper before us. So this was in these years, in 2003 by Ancini, Brades and Cadopiat, but it was different in that they did not have oscillations here. They had oscillations in the regularization term in here. And that's a fundamentally different problem, because here we are going to have competition between W trying to be at the bottom of the wells, but at the same time oscillating very fast. So it's a completely different phenomenon. Okay, I don't want to spend time on this. Source of anisotropy, why is that? It's because suppose that you have a point on your interface. Now zoom in, so you flatten the interface, right? And if you are so lucky that the normal to the interface is, say, En, so it's one of the directions of periodicity of your W, then you just paved, you pave locally the interface nearby with copies of your cell problem, which I went really fast there, but this is basically, you have multiples of the cube with two normals oriented like nu and minus nu. That's the value of the anisotropy at the normal nu. And so basically you have the cell problem with larger and larger and larger cubes, and you have to normalize, because in the end it's going to look like surface energy. So you normalize by the energy of the interface. Okay, so again, if the normal is like that, you just put copies of those cubes that give you sigma, you add them up. While here, if it's skewed, that's no longer true, and you're going to see the anisotropy and the angle coming into place. Okay, so the roadmap for this problem is the usual one. Usually, I showed you that for gamma convergence, there are two properties. One is a gamma limitive, and the other one is that you can find a recovery sequence. Normally, the recovery sequence is the easiest way. It's the easy part, because once you have once you have a conjecture of where you're going to land, you basically reverse engineer that, and you can find your recovery sequence. In this case, it's exactly the opposite. We kind of knew what was going to be the effective energy, but we had to work hard to find the recovery sequence. Okay, but again, I want to move on. And the supercritical case. The supercritical case, now it's a case where you have delta going to 0 much faster than epsilon. Now delta is, again, it's the homogenization scale. So delta going to 0 fast, in our minds, that means that when you take your energy, I don't know if I have it written here, no. Okay, but anyway, so yes, it's in here. So if this goes faster, this basically, what you expect it is going to homogenize like so that this variable is going to disappear. It will only depend on you through this typical homogenization formula. And so if that's true, then in the end, then I mean, grosso modo, but ideally I could replace W by W ohm, and now you're back to my first slides, basically. Then you're back to classical Cahn-Hilliard, no homogenization, you just land on interfacial energy. Okay, so before us, there was work by my former PhD student and Cindy Brady's Piat, where they actually validated what I just said, except that they had to, there was a gap because their delta was considerably smaller than epsilon. Now we can do this whole program just with this condition. We don't have a gap anymore. The techniques are completely different. And in terms of hypothesis, this is extremely mild. Again, it's a Karateodori function, so just measurable in X as it should be. It's basically locally bounded, which is, again, innocuous, should grow at infinity, which is fine. And again, you can do this for multiple wells. I'm doing 2 wells here. You could have multiple wells. P equal to 2 is not, there's nothing magic about it. You can take any P. Actually, any P bigger than 1 will do, strictly bigger than 1, and so on. So you can do all kinds of variants on this. Okay, and indeed you get what you expect, right? You get that the gamma limit is exactly back to the first slides where you have perimeter times a constant, and the constant is explicit as it was before, and except instead of W, put the homogenized, which I showed you before, how you calculate homogenized W, and that's classical in homogenization theory. So the strategies here is completely different from everything we had done before. And what we'll do is that you look at our energy and we perform what we call the unfolding. That is, unfolding is just a method per which you change a very fast variable like X over delta into a macroscopic variable. The price to pay is that now you have a double integral here. You don't mess up with the gradient. This is just depending on X. But W now is going to depend on Y and on X. So you're going to have 2 variables there. It's a very powerful method, which I don't want to go through that, but it's not. It's due to Sioranescu, Damlan, Grisot, and then Visintin independently. Again, it's a way per which you unfold variables which are varying very fast. These operators, so the unfolded, has very interesting properties. For example, it behaves very well with respect to gradients, and so on and so forth. And so it's a very powerful technique. So we use it here, and it worked well. And now I want to talk about the supercritical case, where now you have epsilon going to 0 faster than delta. Epsilon, remember, it's basically the width of the interface, of the transition layer. So morally, what's happening here is that morally you first have the interface, so Cahn-Hilliard going to a surface, but you still have homogenization there. That's horribly complicated, right? Okay, so we have addressed 3 regimes here. The first 2 are in this paper, which is to appear. The last one, we are writing, it's done, but we are still writing it. But I'll go over that. Okay, so you could have, this is a case where you have so wells are moving on you. You have finitely many wells, very general. Again, epsilon goes to 0 faster than delta. And our first question was, okay, so even before I scale this by epsilon, so let's look at the 0 limit, gamma limit here. I should say that before us, with no moving wells and no homogenization, this was performed by Bouchité and our former postdoc and student of at CMU. So, okay, so we decided to then look at just the 0th order term. Again, conditions are very, very mild. In particular, the wells do not have to be well separated. You could have overlapping of the wells, okay? This was quite different from, okay, I should have said that they didn't, so what Bushiti and they did, so they did so there was no term X over delta. Well, yeah, there was no delta. They did just this case, but with moving wells. So the wells were depending on position, but no homogenization. Okay. But their wells were separated. Ours are not well separated. They can be, we can have overlaps. Again, nothing particularly mysterious about two. Just put the P bigger than one, it's fine. But this is just for the sake of exposition here. Okay, so we look at the zeroth order term. And that was pretty involved, but it was okay. And in the end, kind of you get what you imagine, that, okay, you're just going to get the term in gradient is going to disappear, right? You're down here. And the other one is going to homogenize. Okay, you do that. And you characterize the minimizers, which now depend on basically two variables. And I should say that this was first done by Gilles Ford and Stefan Müller for the case of gradients with a completely different method than ours. But they stopped there, so there was no more scaling in that work. But now we keep going, and I say, okay, so let's see what's the next scale now. The next scale, you do a background of the envelope calculations. You have your cell. I want to have A and B. I want to match some kind of a boundary condition. You plug that into your energy. You stare at that for a little bit, and then you say, oh, okay, so let me factor out an epsilon over delta here, and you do, and you get that. And then you say, oh, but wait a second. Epsilon over delta goes to 0, right? That's my regime. So this term is innocuous. It's going to disappear. And this and that look exactly like Cahn-Hillier again, right? Something that goes to 0 plus its inverse. It's exactly Cahn-Hillier. So up to material constants. So you do that. You go to your energy, divide by that, and you realize that what you have is exactly the scaling that work on lipid raft membranes, lipid rafts that I showed you on science. There was exactly the scaling that they were using. It was a bit mysterious, but now we understood why, right? So how do we do this? Now we're going to, again, use the unfolding operator, except now we unfold both. We unfold both terms. And indeed, we proved by doing this, I don't want to, well, okay, so there's going to be a bit of work concerning these degenerate geodesics that basically connect a point in one phase with a point in another phase. They are degenerate because these W's are 0. They have huge patches of zeros, right? So there's a whole work on these. Some of it had been done before by Peter Sternberg and his group in Indiana, and we used those results. And indeed, we proved exactly what those guys said, which was, oh, actually, in the limit, you don't see surface energy, you see bulk. And indeed, we see bulk. The gamma limit is not an integral over an interface. It's dx, it's volume. Where you see the phase separation is at the level of the integrand, because this involves the jump, given a function v that connects two wells. It's going to have a jump set, that's J of V, and then you have this geodesic distance between how you go from one side of the well to the other side of the well, one trace to the other trace. So this is at this level that you see the phase transition, but not at the macroscopic level. Okay, this is just what I just said. What are we studying now? So, okay, so still in this regime, the zeroth order term, I showed that to you. This scaling, I just finished that discussion. And now we are scaling by the usual one, 1 over epsilon n. That's what we're doing now. And this opens a completely different can of worms, because all the techniques we used until now cannot work. And we actually went back to PDs, to the work of Luis Caffarelli, Rafael Lalave, and many other people, Chambol, Di Luciano Vaga, where they actually, why? Because, again, morally, first you go to a surface, and then you have homogenization occurring on the surface. And from the PD point of view, there's a lot of work done on that by these people, which have to do with a notion of plane-like minimizers and so on. And so we had to go back to that source, and it's finished, and we are writing it now. Okay, so there are many open problems. I mentioned stochastic homogenization. So there's work by Esposito, Marziani, and Zepieri, a little bit following what we've done, but in the, okay, that's for those of you who are familiar, in the Ambrosio Tortorelli kind of context. And then you may ask, okay, what about gradient flow? Why don't you let this evolve by surface diffusion, right? Yes, we've done that. We land with Alan Kahn. I've done that with Rassam Shotzi, Jessica Lin, and my former postdoc, Raghav. In a very particular case, where the W is actually a product of a factor that depends on x over delta times a function that depends just on u. It's decoupled. Well, it's the product, but they're decoupled. Plus, we needed a very high regularity on x, which is not a good idea, but that's the best we could do. Independently, this was also done by Peter Morphy. This was his PhD thesis with Takis Souganidis and Takis Souganidis. We work on the same problem, completely different techniques, and we both publish on the same issue of Koch, Vine, PDE, same year, same issue, same problem. Completely different, and by the way, same conclusions, obviously. So, well, you never know. Okay, so with this, I want to very briefly move on to denoising. And you may recall that Gita had a similar model for denoising. So that's the cost function. That's the regularization term, which in my case is just total variation. And here again, the square there's nothing particular about the square. You can put p bigger than 1. This is the fidelity or data fitting term. This is again the regularization term, and alpha is a tuning parameter. Of course, depending on alpha, either you over smooth the reconstruction or conversely. So what is the point here? The point here is that you're given a noised image, which is this U sub beta, and you try to use your TV model TV for total variation to denoise and get as close as possible to the ground truth. So here is a picture where this is a clean image. We messed it up, so you just put some Gaussian on top of it, and then we use the TV to reconstruct. It's not too bad, but you can see there's a lot of staircasing here, but that's the problem with TV model. To resolve staircasing, one possibility is, for example, using higher order derivatives. But it does a pretty good job. But the question is, what is the alpha, right? And until recently, the alpha was, we would find alpha case by case, depending on the picture, and you want to have a more automatic way of doing that. And you do that by thinking of essentially a learning scheme, in this case, with 2 levels. And this is how you go about it. So I'm going to have a collection of training data. So I know what U sub C is. It's my clean image. I deliberately messed it up. U eta is the noised one. So you start by, for alpha fixed, you take a minimizer, for which of course exists. And then you say, oh, okay. So now let me look at the cost function, which is the L2 norm between what I found and my clean image, and what is the best alpha that lowers the cost, right? You can be ambitious. I don't want to go through that, but if you want to include higher order derivatives, go to the so-called TGV, total generalized variation. You can do that. I'll show you some simulations with TGV, and basically you're adding a symmetrized second order gradient to to the energy. Okay, and again, also in this case of TGV, you're going to have two parameters, alpha and beta, and you may ask the same question, what should alpha and beta be? But also, you see, even in TV, just for first order, maybe the weight should depend on where I am, right? So, for example, if I have a picture with a huge, with a huge area where there's a huge cloud, maybe I don't need a lot of detail there, right? But if there are other places where I need more detail, then the weight should depend on position. And that's exactly what this is. So this is the weight, and that's the way you write TV for depending on position. And, well, of course, if the weight is bounded away from 0, you're back to BV. So there's nothing particularly interesting about that. So, so what we're going to do is the following. And this goes back, again, to the people before us who thought about doing these kind of decompositions and working with weights. So what we do here is, so I have basically my cartoon. I'm going to put a dyadic grid in there. So Q's, so these are small rectangles, disjoint except maybe for overlapping of the edges, different sizes. And so I am going to, I think I have a picture here. So think about it like that. So some places I could keep subdividing, other places maybe not. So it's going to look like something like that, right? Dyadic. And okay, so then you can think about it by saying, okay, so now I'm going to have 3 levels to find the parameters in that, because now you have 2 questions. What are the parameters, which probably depend on the little squares or that you have in your subdivision, and what is the best grid, right? So you have the 2 questions. So, okay, so first, let me fix one square inside my grid. Again, I'm going to find U alpha to be the minimizer for that. Then I'm going to minimize over all possible alphas for that particular L. Now, with this, I now get a weighted function, a weight function here that depends on wherever I'm on this square, I'm going to have a corresponding weight alpha L, which I got from level 3. And then you minimize again. But now with these weights, again, the cost function and the weights, and then you come here and you have level 1, where now you got this candidate, and you're going to see about, among all possible ways that I can subdivide my cartoon, what's the best one? So you're going to minimize over that. I'm about wrapping up pretty soon. Again, many people have worked on this kind of multi-level training schemes. By no means I am being comprehensive. Again, we have already 1 paper out. We have another one submitted, which I should have written here. But okay, so you can ask, right? So do these problems have a solution, right? So for example, how do I know that I don't keep subdividing my grid and I will never converge? So there are ways in which you can assure that, and one of them is, okay, so anyway, there are good news. There are ways in which you can do that, and one of them is by massaging well the initial data. So you can do that. Okay, so that's another technique which is modifying the weights. But another way also to treat this is, instead of putting, I had an alpha here, right? In terms of minimizers, if I divide by alpha, I have the same minimizer, right? So called lambda would be 1 over alpha, right? I didn't change the minimizers, but it's going to change the problem by having now the unknown parameter in front of the cost is going to completely change or change considerably the problem. Okay, and then you can play the same game, right? You have, again, 3 levels, except that now you're going to try to find out what are the lambdas that you should put, and again, you're going to have a lambda in the end. It depends on the composition of your grid, and then again, you end up with level 1. Okay. So again, as I said, there are ways in which you can guarantee that this process converges. And one of them is to start with training data, which is well prepared. But okay, that's a theorem. Okay, so finally I have just a couple of pictures. Let me show here. So this is TV global, so there is no weights. That's a typical cameraman picture. This is the clean image, messed it up, and this is what you got with now with the tuning parameter lambda in front of the cost, right? So that's what you got. Eventually, I'm going to tell you what are the errors that you make. But then again, I want to now start subdividing, right? This one, it was global, so I had no subdivision of my of the rectangle of the cartoon. Now I'm going to start subdividing, right? And I subdivide more, and I subdivide more because I want what I want more detail is here, right? Is on the cameraman. So I keep doing that, and then okay, and then after that, when I'm getting there, then I realize that if I look at the cost, remember the cost is the difference between what I call U star, which is what you get at level 3, and the clean image. And you see that with just lambda, just with the lambda, you get this is the cost. While if you do weighted TV, so actually on each position, you change the way your lambda, the value of your lambda, you do much better, right? So the cost is much lower. Okay, now you may ask, okay, so I showed you the weighted TV, so with the parameter alpha, or then the multi-level training scheme by putting the parameter in front of the cost function, there's no big difference between one and the other in terms of the cost, right? Okay, now what about TGV, so second order, right? Do we gain anything by doing second order, which is of course much more consuming? And again, not really, right? So this is TV, this is weighted, this is weighted TGV, the cost is not that different, right? So putting higher order does not seem to be a big deal. And finally, there's a lot more to do. Right now, still with Elisa and our collaborators, we are now beginning to study multi-level training schemes for Mafercha. You could think about, by the way, all this is scalar valued, so black and white and grays, so no colors. And it's not that we can mutatis mutandis go to colors, no. So you could think about RGBs, red, green, blue, so say values in R3. So it's a different ball game, so we have not done that. And I think that with this, it's a good place to stop. Thank you.
Thank you very much. Questions?
Yeah, so with this training that we have, at some point we decide on the values of these parameters alpha, betas, gammas. And I expect that all these pieces will talk about different features of the picture. So maybe some hedges.
Oh, the weighted ones, yes.
And if we train it, then we train it on some specific set. And then we have to be sure that the picture that we feed the machine is going to
Well, okay, so that's a very good question. So you have these huge sets of training data. And then the question is, suppose that now you take a picture that you don't know what is the clean image. How am I going? And what you do, so the way that you fit that into one of those classes so that you are as close as possible to one of those training pairs is by using neural networks. And that's exactly what you do. So that's a good question. Sergio Conti asked me the same question, so now I was prepared.
Further questions?
In the first part of your lecture, you said you took p equals 2, but you said you can also do p bigger than 1. And then in the second part, you do BV. Is there anything known sort of about convergence results if p tends to 1?
Yes. The short...
Okay, the short answer is yes, it's very hard to do it because, of course, you're going to leave some left and you're going to end up in BV. It's been done in very, very particular cases, definitely not with homogenization. So you have to go back to Kahn-Hilliard, right? Homogenization with P, because then you have three effects. You're going to have going to surface energies, you're going to end up in BV, and you have homogenization. No. But the Kahn-Hilliard, yes. So if you have a P that goes to 1, you can do that. Yes, but it's a lot of GMT, but you can do that.
If there are no further questions, so thank you very much, Irene, once again.